Hopefully this video is going to work better. Yeah, I think the light was just too low. It used to work like that. So if you put your homework away, get it back out. And I don't even know that having this up here on the screen is that helpful. A force, according to the book, is a push or a pull. And he also defines it as any influence that tends to accelerate an object. So if something is accelerating, there's a force acting on it. The second one, he talks about acceleration being directly proportional to force, and he talks about mass being inversely proportional to acceleration. What he means is that since F equals ma, if you make the force bigger and you keep the mass the same mass, what does that do to the acceleration?
Increases it.
Yeah, in order to multiply mass by something and get a bigger force, that thing that you multiply the mass by has to be bigger. So this is just another way of saying if I'm pushing two objects, let's say I'll push this hammer with a force. There's enough to do that. I'm going to push the table with the same force. Nothing happens. So because this has more mass, it accelerates much more slowly with the same force. That is less mass, so it accelerates faster. If I push the wall, which has even more mass, it's going to accelerate even more slowly. More specifically, if I push with, sorry, I'm doing the wrong one. I'm doing the next one. I'm getting my video all confused. Let me get back to this one. This is just saying if I push with more force, so here's what I should have done. Hammer again. I'm going to push my hammer with a small force. Now I'm going to push my hammer with a big force. Didn't mean to push it into that. I need to get some better objects to push it. I'm going to break something. So if I push with twice the force, what does that do to the acceleration? It doubles it. If I push with 3 times the force, what does that do to the acceleration? Triples it. So whatever I multiply my force by, I'm multiplying acceleration by the same thing. And I'll put a link to all these answers on my website. They're too small to see right now. I apologize for that. So that's what directly proportional means. When you have an increase in one thing, the thing that is directly proportional to increases by the same factor. Now, this is kind of what I got off on a second ago. If acceleration is inversely proportional to mass, that means bigger things are going to accelerate slower. And if I push on something with the same force and the object is twice as massive, then the acceleration is going to be a half. If I push on something and the mass is 10 times as massive, what is that going to do to the acceleration? It's going to be 1/10 of what it was before. So instead of multiplying by the change in mass, you're dividing by the change in mass. When something gets bigger by a factor of 6, you divide by a factor of 6 to get its new acceleration. Number 4, which way does friction always act? It doesn't always act northward or southward or eastward. It's always opposite motion. So if I push this table to the left, friction's pushing to the right. If I go over here and I push the table back to your right, then friction's fighting me and pushing it to the left. Whichever way I push it, friction's going the opposite way. Which way is friction acting right now? It's a trick question. There really isn't any until you attempt to do some pushing on it. Friction kind of waits to pop into existence as soon as something tries to push something else, slide it around. 5, what causes friction? According to the book, what causes friction? Somebody just blurted it out.
Differences in surface.
Little bumps, microscopic bumps on surfaces. The weight sitting over there on the table, it's got a little hook, looks like that, it's sitting on the surface. If you would zoom way in, then the bottom of this weight would kind of look like this, and the surface of the table would look like that, and these little bumps would intermesh with one another so they wouldn't slide back and forth very well. That's part of what causes friction. There are also intermolecular attractions, maybe some positive charges on this and some negative charges on that make things stick. Certain types of materials are stickier even when they're equally smooth, like rubber. You have smooth rubber, smooth wood, rubber is going to have more friction. But the book only mentions microscopic bumps on things, so that's good enough for me. What's friction called when something's rubbing against air? Air resistance. Does anybody know another name for that? Another word for it? It's also called drag. You don't need to know that, but it is. You could say air resistance or you could say drag. The next question was a really bad question. I typed it up. I take full credit for this bad question, and I apologize. But let's talk about the answer. The question was, it said something like, in the following examples, circle the letter of the situations where friction is in action or something like that. Is that what it says?
When friction actually affecting the outcome.
Yeah, so circle the situations where friction actually affects the outcome. And it doesn't say situations, it says circle the letter. Turns out that there are 3 different situations. So I want to rewrite the question right now. You don't have to change it, just think about the answer. There are 4 situations that are described there. In which situation is friction doing nothing? So in other words, friction, you could have friction, you could not have friction, and you wouldn't be able to tell a difference. Guess which letter that's describing? That would be letter C. So if you get that, then you understand the question the way it should have been written. And if you still don't know what I'm talking about, I want to try to clarify now. So,
C is right or C
the
is
C, yes, bad question. C is the only situation where friction's actually not doing anything. Friction is not affecting this situation. If there's friction here, if there's not friction here, it has no effect on what you would see. So, for example, it says a box is sitting motionless on a level floor. Here's the box, here's the level floor. We see it there. Just by looking at that, can you tell me, is it frictionless or is there friction? Can you not tell? What would happen to this? If this is perfectly level and there was no friction between the box and the floor, what would happen? It wouldn't move, right? Because it's perfectly level, there's no reason it would move. Now, what if there is friction between the box and the floor? What would it do in that case?
It would have to be moving.
Wouldn't move, would it? So you've got a box on a floor that's flat, and there's friction between the box and the floor. It sits there. You've got a box on the floor the floor is flat. There's no friction between them. It sits there. So if I'm not pushing that box, if the floor is level and nothing's pushing the box, friction doesn't play any part in this. Friction has nothing to do with it. All these other situations, friction is doing something. In situation A, a box is on a level floor. You're pushing the box sideways, but your force is too small to move it. I'll just imagine this as a big box. I'm pushing on this. If I pushed harder, I could move it, but I am pushing and it's not moving because of friction. If there weren't any friction, what would happen here? It would start to move. It would accelerate and get going. So in that situation, friction is involved. So the way the question was written, you were supposed to circle that one. The second situation, the box is on a level floor. You're pushing the box sideways, causing it to slide. I'm just going to demonstrate with this. Is friction involved in this situation right now? Yeah. If there weren't any friction, what would this table do? It would slide easily and it would go faster and faster and faster. Right now, I'm pushing just hard enough to overcome the friction, but I'm not actually accelerating it. And if I let go, it stops. So if you're pushing a box across the floor, causing it to slide, then it's friction is at play there. And in this last one, a box is motionless on a tilted floor. If I tilt this thing isn't moving. That tells me there is friction or no friction. Friction. If there weren't any friction, it would just slide off. That's a dumb question. I apologize. I just wanted to get past it so you wouldn't be kind of stuck on it forever. The next one is okay. In light of the previous question, in what type of situation does friction affect the outcome? And the answer is friction comes into play anytime something is sliding or tending to slide. You don't really have friction until something starts to slide or it's pushed to try to make it slide. So the only situation before where friction's not doing anything is where it's on a flat level floor and nobody's messing with it. Okay, that was those are not very good questions. This next one, this is a good question. This is asking, why do things fall at the same rate? And it's a good question because if you have a large steel cannonball and a small steel cannonball, the weight of this one is going to be really heavy. Let's just say it's 100 newtons. And the weight of this one is only 15 newtons. That's the force of gravity pulling them down. Now, if there's no air resistance, which one hits the ground first? Let me start them out from the same height. You drop both of these balls. Gravity pulls this one with a really big force. Gravity pulls that one with a smaller force. Which one hits the ground first? Hit at the same time. And the question is, how can that be possible? How is it possible for everything to fall at the same rate? I've told you that the acceleration of gravity is always, always, always 10 meters per second squared if there's no air resistance. But how can that be when this is pulled so much harder than that? Andrew?
It's pulling an object with a bigger mass.
Exactly. So that's it. This has so much mass and inertia that even though it's being pulled with a greater force, it's harder to get it moving. This is being pulled with a smaller force, but it has less inertia. So in the end, the little thing with small inertia being pulled with a small force is going to move just as fast as the big thing with lots of inertia pulled with bigger force. So everything falls at the same rate.
Isn't the weight to mass, like the proportion the same to the ratio?
Yeah, it is. And I've done this in every class. I'm going to do something kind of stupid, but I'm going to do it's maybe there. After I do it, you tell me whether there was any point to it. So what I'm going to do is calculate. Start with their masses. I'm going to say this is 2 kilograms, this is 10 kilograms, and then I'm going to show why they hit the ground at the same time. So the first thing I'm going to do is calculate their weights. The weight of this is the force of gravity. What's the formula for force? Mass times acceleration. That'd be 2 kilograms times negative 10 meters per second squared, which is the acceleration of gravity on Earth, which would be negative 20 newtons. So this arrow going down, that's 20 newtons. I'm not going to write this out, but I'll just multiply this mass times the acceleration of gravity on Earth. 10 times negative 10 would give me 100 newtons down. So if this is 10 kilograms and that's 2, we've got a 100 Newton force pushing this down and a 20 Newton force pushing that down. Now I'll take those forces and I'll use Newton's second law to calculate the acceleration of each of those. I can rearrange this to acceleration equals force over mass. So if I calculate the acceleration of this going to the ground, 100 newtons divided by 10 kilograms, I get 10 meters per second squared. If I do the same thing with this one, the acceleration is the net force, 20 newtons downward. divided by mass, 2 kilograms, and I get 10 meters per second squared. So both of them accelerate toward the ground at the same rate. The dumb thing about all this is I just went in a big circle. I used Newton's law to come up with this downward force acting on each of them. And then I took that downward force, put it back into Newton's second law to get the acceleration I put in at the beginning. Was that worth it? I don't know. Maybe it helped, maybe it didn't. But what this shows, if you're calculating an acceleration, to get the acceleration, you're dividing a force by a mass. If you divide a big force by a pretty big mass, you get 10. If you divide a small force by a small mass, you get 10 also. So it's I think, was it Kara? Somebody was just saying, it's the ratio of the force pulling down to the mass that gives you the acceleration. And stepping back, maybe I should have just said what it says up there. Friction, no, that's not what I should have said at all. More massive objects have more inertia, so even though gravity pulls on them with more force, they don't fall faster than small ones. Now I want some answers from you. Got a plastic ball, and it's falling out of the sky, and it has a terminal velocity. The terminal velocity is the velocity when air resistance pushing up equals the weight of the thing pushing it down. So I want somebody to tell me how I can increase the terminal velocity. There are 2 different, fundamentally different ways to do it, maybe 3 even. Sam?
Change its weight.
Change its weight. Would you make it heavier or lighter? So if you filled it with lead, put a bunch of little lead shot in there and you increase the weight, then weight would suddenly be stronger than air resistance and it would speed up. So that would work. Without changing the weight, what else could you do? Anybody else have a blank?
I think you can like hit it harder with more force.
Well, if you're talking about a ball that somebody hit, if I get in an airplane and I hit a ball downward, that doesn't actually affect its ultimate terminal velocity. If I got it going faster than its terminal velocity, it would just slow down and it would reach the same point no matter how hard I hit it. And the terminal velocity is dependent on not how fast it starts out going, but the air resistance pushing up and the weight pushing down. So I could change the weight, or I could change what? What else could you change other than the weight of this? If I am jumping out of an airplane and I decide I'm not going fast enough, what can I do?
Oh.
I can tuck in, I can form myself into a cannonball, and which of these 2 things is that affecting? That's affecting the air resistance. So one thing you could do is you can compress the ball. Another is you could somehow shape it into a teardrop or something to make it more aerodynamic. But whatever you do, you could either find a way to decrease the air resistance, or you can increase the weight, or you can do both. And then a third option, did you hear about Felix Baumgartner last year?
Yeah,
Yeah.
that was
What?
amazing.
He jumped out of a capsule from a balloon about 24 miles up. And he broke the record for the highest parachute jump, also for the fastest that any human has traveled not in a vehicle. He went over 800 miles per hour. So normally, if you jump out of an airplane, you can fall at about 120 miles per hour.
Good for
How did he get up to 800 miles per hour?
Is that good for you?
If you survive. Yeah, he had a pressurized suit, he had oxygen. So guess what he did that made him go so much faster than this?
Put lead in the suit.
What's that?
Put lead in the suit.
No, he didn't add weight. He didn't really make himself more aerodynamic.
Can you have himself more around the
Yes, sort of. He was up really high in the atmosphere. What's the air like up there? Thin. So the air resistance was really small because there wasn't much air.
So the higher you go.
The higher you go, the faster you can fall.
Temporarily.
We'll watch that video. We can watch a video of it in a minute. So my answer to this, I actually gave 3 answers, but 2 are fine. You could increase the ball's mass without changing the size. You can decrease the ball's size without changing its mass. So the first one increases the weight, and the second one decreases the air resistance. And I added in a third one, which is drop the ball in air that's less dense. If you drop it higher up, then it'll work. Number 11, why does this work? Increasing the mass increases the force pulling it down. Number 2, decreasing the ball's size, that decreases the force pushing it up. And my third explanation, dropping the ball from higher up means there's going to be less air resistance because there's less density. For these next ones, there are 3 different situations, and I want to hear from people what they thought the action and reactions were. The first situation, we have a car, and the car is driving forward. So let's make the car go this way. There's an action and a reaction. This is the kind of answer I'm looking for. When I jump, I push the floor down, and the floor pushes me up. So one is me pushing that way, and the other is the floor pushing this way. So Charlotte, do you have any idea on the car? Action and reaction? Yes. Which way do these tires rotate? Anybody? Clockwise or counterclockwise? They're rotating clockwise. And the important part, the place where this is really happening is right here. Right there, the rubber part of the tire pushes the road this way. It pushes the road to the left, and the road pushes the car to the right. What would happen if you put this car on top of a board, and under the board you had little logs so that the road could actually roll around? Which way would the road go? The road would be pushed to the left and the car would go to the right. It'd be kind of like that catapult I showed you in class. But the road is so heavy in reality, the road is attached to the earth, that the road doesn't actually move backward much. The car goes forward and the road, you don't even see it move. The second one, this was about a rocket blasting forward. And I'm going to, let me know what I did with this. By the way, is this somebody's bag?
I think it's the teacher that
This, yeah, that could be hers, Miss Bessie.
it was.
I'm going to draw this as a water rocket. It doesn't have to be a water rocket. If you answer this from the book, you'll have an answer that doesn't really apply to a water rocket. So the water rocket goes this way. Can anybody tell me what the action and reaction are? Like such and such pushes this way, and this thing pushes the other way.
Air resistance push it down.
Sort of.
The water
The
pushes
water
down.
pushes it down.
Well, in the case of this rocket, let's divide it into the water and the rocket. Those are the 2 things that are really involved here. They're pushing one another. Which way does the rocket push the water?
Yeah.
The rocket pushes the water down. And which way does the water push the rocket? Up. And this would happen in outer space. If you had a water rocket, it's throwing mass out the back, and that process pushes it forward. People used to think that rockets wouldn't work in outer space because they thought a rocket was like a bird. A bird was, that, and it pushes the air down. If I could do this fast enough, it would be really cool. It pushes the air down, and the air pushes it up. If you pump it'd be a nasty trick to birds. Say some birds are flying by, and we hook up a little vacuum hose and we suck all the air out of the world. What happens with birds? They crash to the earth because they're pushing against the air. It'd be like you're swimming along and suddenly the water's gone. You just fall to the bottom of the ocean and splat in the mud. So, but if birds were like little rockets, if they were constantly shooting mass out of their cloacas, then they would be propelled forward. And if you got rid of the air, they'd still be okay. Like, all right, let's move on. This last one, this is the most bizarre. It sounds like the most tame, but this is the earth. Actually, I'll just use my pen. I'm gonna let go of it. So in the question, this was a ball falling to the earth. What's the action and what's the reaction? Anybody? I won't call. Sam. Yes? Yes. So when I drop this pin, there's a gravitational pull between the pin and the earth. The earth pulls the pin down and the pin pulls the earth up. And so why doesn't the earth just hop up in the air if that's happening?
Its mass is great.
Its mass is greater. The same force though, there's the same force pulling this down that there is pulling the earth up. The earth has so much inertia that it doesn't move much. I think the next one's related to bullets and guns and stuff. Yeah, number 13. So you shoot or somebody shoots a gun up in the air or wherever. Here's the gun. Gotta have a trigger for a gun. And a bullet goes down the barrel and then comes out. Here's the bullet flying through the air. The bullet goes that way, what does the gun do? Goes the other way. If you've ever shot a gun, guns kick. When you shoot, the gun comes back like this and the bullet goes out like that. The question here is, if this is super fast, this might be 3,000 feet per second. For some reason, bullets are measured in feet per second usually. The gun doesn't move nearly that fast, maybe 5 feet per second, initially. If these two forces, the forces pushing the gun to the right and the bullet to the left are supposed to be equal and opposite, why does the bullet go so much faster than the gun?
Because it's smaller.
Because it's smaller. So the bullet has less mass, the gun has more mass. The same force is going to push something with less mass a lot faster. The acceleration is inversely proportional to the mass. So if the mass goes down, the acceleration and the speed go up. If the mass goes up, then the acceleration and the speed go down.
5 feet per second as recoil.
I'm just kind of making that up. I'm pulling that number out of wherever. So if those little birds, if those birds were armed with machine guns and they're flying around and then somebody pumps all the air out, what could they do? Which way should they shoot?
Down.
Down. Because then the water going down would shoot them up. And
It's like slaughter a good 20 people though.
yeah, that would be revenge on the people who pump the air out of the atmosphere.
Maybe good.
The last ones, these are about vectors and scalars. A vector quantity has magnitude and direction. An example of a vector quantity is 50 newtons upward, and a scalar quantity just has a magnitude. An example of that would be 50 newtons. You don't, with a scalar, you don't know which way it's going. With a vector, you could put an arrow to it. And the very last one, number 15, there were 4 different quantities there, or different units, or different parameters. Which one can be a scalar? Which one is always a scalar?
Velocity.
Not velocity. Velocity, remember, has direction. And
Oh, a scalar.
which one's a scalar? There's only one.
Acceleration.
Not acceleration, because acceleration is
Yeah.
negative if it's down, positive if it's up. Speed. The only one that's always a scalar quantity is speed. The rest of them, we will be using arrows to show their direction. We'll never show the direction of a speed. I've got a couple of things I want to show you. I'll turn this off though. Don't need to be.